All right, so this brings me to the second half of the chapter, which is based on buffers. Now, we have already seen the importance of aqueous solutions in chapter 15 and in the earlier part of this chapter. And now I'm going to focus on buffers, and then later on, we are also going to talk about the pH metric titrations, use of a pH meter, how we run the math, etc. So, first things first, what is a buffer? Um, is nothing but something that resists a pH change. So buffers resist pH change. So you might wonder, how is it that they're going to do that? First off, buffers are important first and foremost, and I'm going to get into how they do that. But why are buffers important? They are tremendously important, especially in biology, because all physiological processes, they occur usually within a narrow pH range. For example, for us, our best performance is seen when the pH is between 7.24 to 7.40. That's a pretty narrow range. It's only 0.16 pH unit. And so it's important to maintain that pH. Any pH lower than that or any pH higher than that can lead to a condition called as acidosis or alkalinosis, which essentially refers to greater amount of hydronium ion or greater amount of hydroxide. That means the buffer, in our case, blood being the buffer, has gotten disturbed somehow. And so sometimes a drastic change in the pH could be even fatal. So you can have symptoms like dizziness and shortness of breath, unconsciousness, and in the worst scenario, it can even be fatal. And so maintaining that buffer for the proper functioning of the ecological system is of utmost importance. It is really important. So to give you a flavor, let's consider the antifreeze ethylene glycol. Ethylene glycol, the structure of that is this compound, and you can perhaps envision that this would be very soluble in water because it has the capacity to form hydrogen bonds at the OH. Now, this is something, if you are wondering, we have talked about this though previously, as to where we use this. This is used in your car radiator in the coolant, and it's used as an antifreeze in the cars as an aqueous solution of ethylene glycol. And so it does have a somewhat sweet taste, and so it can attract, small pets or even young children who could be vulnerable to this toxic compound. Now, the first stage of this glycol poisoning resembles like a state of drunkenness, and later on, if left untreated, essentially this could lead to more problems. Now, how does ethylene glycol metabolize? In liver, ethylene glycol gets oxidized into glycolic acid. So one of these OHs gets converted into COOH, and it enters the bloodstream. Realize this is a carboxylic acid, so this is acidic, and this is going to drop the pH of the blood if the blood were not a buffer. So depending on the amount of the glycolic acid that you have, realize that blood itself is under a very tight, while ecologically, physiologically, most of our cells are between 7.24 to 7.40, blood is between 7.36 to 7.42. So it's tighter. And many proteins essentially require this narrow pH range for their proper functioning. And if this glycolic acid enters the bloodstream, essentially there can be a problem, because if the concentration of glycolic acid is too much, then the buffer may not be able to resist that pH change. Realize that you have H2CO3 carbonic acid, which in presence of base would give you water and bicarbonate. And this bicarbonate is going to neutralize the protons provided by the glycolic acid, the H plus, to give you H2CO3 back. So in this way, the carbonic acid bicarbonate buffering system keeps the pH blood or pH of the blood constant. Now, if the concentration, like I was saying, if that concentration of glycolic acid becomes too much, then the blood pH is going to drop dangerously low, and that kind of situation would be called as acidosis, and this is going to affect the ability of hemoglobin, for instance, to be able to carry oxygen. So just to give you a flavor, hemoglobin in the protonated form picks up the oxygen and carries oxygen while it delivers the proton off. Now we are saying that glycolic acid is present in the system. That means we are able to pump in protons into the system. And so according to the Le Chatelier principle, hopefully you can see that a backward reaction will be more pronounced. That means the ability of hemoglobin to pick up oxygen is going to be diminished. And so if that is the situation, then your pet or the child would be hyper ventilating in an effort to overcome this acidic blood's lowered oxygen carrying capacity, and if left untreated, the results of the situation could be really bad. And so to the extent that it could be fatal. One treatment for ethylene glycol poisoning is the administration of ethyl alcohol. Ethyl alcohol is essentially your wine, what is present in any alcoholic beverage for that matter. The two molecules are similar. The only difference between the two is that one contains only one single OH, the other contains two hydroxyl groups. But the way the two are metabolized is pretty different. So essentially, the liver enzyme is going to, P450 is going to work on ethanol as well, but it's going to generate, either it's going to go through the body unmetabolized, or it's going to generate acetic acid, which by the way is also generated naturally in our system. So it's not going to be, it's going to be excreted through the urine, and we are not going to see these kind of effects that we see for the case of the glycolic acid generated from ethylene glycol. So again, I gave you the entire story about buffers, gave you an instance of that to make you understand that buffers, the primary reason for that is, for the existence of buffers in nature, is to resist pH change, because essentially nature would want to protect itself as much as it can. Now, you might ask, what does the buffer contain, and how does the buffering action take place? And like I said earlier, a buffer contains a weak acid and its conjugate base, or it could contain a weak base and its conjugate acid. So either it will contain a weak acid with its conjugate base, or it would contain a weak base with the conjugate acid. Both of those can act as buffers. For example, in the previous slide, I gave you a situation where I had carbonic acid, H2CO3, and I removed the proton and gave you bicarbonate. So that's one buffer, right? So that's the weak acid. That's the conjugate base associated with it. You could have ammonia with ammonium, where ammonia is your weak base and ammonium is your conjugate acid. So a weak acid by itself, even though it partially ionizes to form some of the conjugate base, does not contain sufficient base to behave itself like a buffer. Similarly, a weak base by itself, even though it partially ionizes water to form some of the conjugate acid, doesn't contain sufficient amount of acid to behave like a buffer. That means a buffer should contain significant amount of both a weak acid as well as a conjugate base. What I just said, again, just to give you a flavor, because we have seen both of those reactions previously. Let's say you have HF. Okay, when you put HF in water, you're going to get a little bit of hydronium ion and you're going to get F minus, but it's not like 100% dissociation because it's a weak acid, right? So my HF F minus system doesn't necessarily have like a boatload amount of F minus. Likewise, if you consider the backward reaction or the fact that fluorides generate a slightly alkaline solution. So if you put that in water, it's going to rip off the proton and will give you HF and OH negative back, right? So F minus is giving you HF, but it's not enough, it's not sufficient. So based on those two reactions that we have seen in the past, realize that HF on its own cannot behave like a buffer because it doesn't have significant amount of F minus ion. It's not a complete ionization, that's right. And the other is that F minus on its own, so sodium fluoride on its own, for instance, is not going to generate enough amount of HF for that matter. And so for that reason, neither the conjugate base by itself nor the weak acid by itself can behave as buffers, but the two together are included to form a buffer. So a buffer must contain significant amounts of the weak acid and the conjugate base are desired. So concentration is a big thing. Okay? All right. Now, suppose you add like a strong base such as sodium hydroxide. Okay, that's a strong base which undergoes complete ionization. And I put it in acetic acid. So I have acetic acid, CH3COOH, and I have sodium hydroxide, and I put the two together. You will say that acetic acid will neutralize the base, so it will generate CH3COONA, and H2O will be generated as the byproduct. So one can say that as long as the amount of the added sodium hydroxide is less than the amount of acetic acid in terms of moles, then the buffer is going to be able to neutralize that. So since we know that acetic acid is going to neutralize the acid, the alkaline part, if this acetic acid is a part of a buffer, so let's say now it's part of a buffer, CH3COOH, and you add the sodium acetate, they are together. If you add a little bit of sodium hydroxide, as long as the moles of sodium hydroxide are less than the moles of acetic acid, essentially that acetic acid should be able to neutralize the added sodium hydroxide. And likewise, if you add HCl to the system, so suppose you added HCl to the system, as long as the moles are going to be less than the moles of the base, which in this case is going to be sodium acetate, because that sodium acetate will react with HCl to give you acetic acid and Cl negative. So with acetate, you're going to get acetic acid and Cl negative. So if it was sodium acetate, that will become NaCl in that case. Uh, so realize that as long as the number of moles that are being added are less than the moles or the concentration of the acid part and the base part of the buffer, we would be able to resist pH change. That means whatever change occurs, it's going to be minimal. That's why we say the resistance in the pH will occur. On the other hand, if you just add too much of the acid or the base, then of course the buffer won't be able to withstand that, and hence, in that case, there'll be a problem anyways. So just to again summarize, buffers will resist pH change. Buffers contain significant amounts of both a weak acid and the conjugate base, and the weak acid neutralizes the added base, while the conjugate base neutralizes the added acid. So let's take a look how we can generate a buffer. And when the two are mixed, essentially the starting point is, how does that change the pH of the solution anyway? So let's take a look at that first. So the solution that is a weak acid and the conjugate base mixture, and which resists a drastic pH change, is what is called as buffer. Small amounts of hydroxide are going to resist, they're going to increase the pH by a little bit, tad bit, but not by much. So let's say the buffer was like 4.78, it might become like 4.80 or 4.81, but it's not going to become 6. All right, and this is because the acid component of the buffer would be able to neutralize the OH for the reasons I explained previously. Likewise, realize that if you would add hydronium ion source, so if you add some kind of an acid, it's going to again decrease the pH, but not by much, because the conjugate base component of the buffer is going to neutralize the added hydronium ion. So that is the reason why you need to have a significant amount of acid and a significant amount of the conjugate base in that buffer solution. That concentration is really, really. So just to give you a flavor, some examples: acetic acid and acetate, HF with F negative, ammonium ammonia. We talked about this in class as well. Realize we would not be able to get a buffer of HBr, Br negative, or maybe HCl, Cl negative. These are not buffers, no. And if you can think of a suitable reason, that reason is that HBr is going to completely dissociate and give you 100% proton and 100% Br negative, the conjugate base. It's too much. There is no acid component left there. All it contains is the conjugate base. So that is the reason why you're not going to be able to use a strong acid for the buffer. It has to be a weak base or weak acid and its conjugate version. And like we've already discussed, I gave you the example as well. Buffers are very important in biological system for proper protein functioning, because proteins, hopefully you know this from a biology class, proteins ultimately depend on their structure, the way they fold, for their functioning as well. And if a protein misfolds, or let's say a particular nitrogen atom undergoes protonation, let's say because of the presence of the added acid, a protein may not be able to fold the way it's supposed to, so it might lose its shape, and if it loses its shape, it probably will also lose its function. So the shape is vital for the functioning of a protein. Now, I'm going to go over, more math problems, I'm going to give you the logical way, and I'm also going to give you the easier way. We are going to take a look at both of those and go with that. I'm going to work on one, and I expect you to work on the other, following the steps so that both of us know how to go about it. All right, the question is addition of hydroxide to a buffer. So if what happens if we add 0.01 moles of solid NaOH to 1 liter of the buffer. So the buffer is already there, and we have added a little bit of the base. Okay, so how do we go about it? That's what we are going to discuss next. Now, what I want you to do is I want you to think about what kind of equilibriums do we have in this buffer. So we have sodium acetate, I said, sodium acetate, which was put in water. That means it gives you so acetate and sodium. And we had taken 0.1, that means acetate is present up to 0.1 molar solution. We took acetic acid. So that's my main ionization, acetic acid plus H2O, giving you hydronium and acetate. And essentially, acetic acid concentration is 0.1, initial concentration. And of course, we are going to use the remainder from what's going on in that solution. We are saying that we have added a tad bit, we have added a little bit of sodium hydroxide, solid sodium hydroxide to this buffer. The amount that we added was 0.01. What does sodium hydroxide do? NaOH. It completely ionizes. It will provide you OH negative and Na plus. How much OH negative would it provide? 0.01. And that OH negative is going to basically react with the acetic acid component of the buffer. And so hopefully you can see a third reaction is going to take place, that the acetic acid, because realize my buffer is CH3COOH and CH3COO minus. So what's going to happen is that this added OH negative is going to react with the acid part, not the conjugate base, but the acid part of the buffer. So CH3COOH is going to react with the OH negative and give you what? It will give you water and acetate. One might ask, how much of acetic acid would react? Well, realize the stoichiometry is 1 to 1. That means if I have 0.01 moles of the hydroxide, 0.01 moles of acetic acid would have reacted, and 0.01 moles of acetate would have gotten generated. What does that mean? That means that if you have to set up your ice, you began with 0.1 molar solution of acetic acid, but part of it has reacted. So you must subtract that from your initial concentration. Hydronium, of course, is still 0. Acetate, you have 0.1 from sodium acetate, but you have also formed a tad bit from this reaction in red. So you must add that 0.01 to this acetate. Of course, the change is going to be the same way. And so your overall reaction is going to be 0.09 minus X at equilibrium, X for the case of hydronium, and 0.11 plus X for the case of acetate. And now if you use these numbers to plug in for your Ka will start looking like hydronium, which is X, times acetate, which is 0.11 plus X, divided by 0.09 minus x. Again, you ask yourself if you can use the approximation or not. So the concentration of acetic acid is 0.1. The Ka value is 1.7 or 1.8 times 10 to the negative fifth, which is way more than 100. The approximation is valid, and so you can neglect the value of x, and you can rewrite this as 1.8 times 10 to the negative fifth is equal to x times 0.11 divided by 0.09. And now we are going to solve. As we solve, x will come out to be 1.47 times 10 to the power of negative fifth molar, and x is nothing but the hydronium ion concentration. So if you take the negative log of this number, 1.47 times 10 to the negative fifth, that's going to give you a value of 4.83. Recall, your pH of the buffer was 4.78. pH of the buffer was 4.78, and it only rose up to 4.83 in spite of adding the 0.01 moles of the base. I want to just give you a scenario just to kind of make you realize what this resistance to pH is. Right now we are saying the change in the pH, it has increased, yes, because you added buffer, but the increase is very, very little. It's only 0.05 units. That's nothing. Compare this to a situation. What would have happened if you would have 0.01 moles of sodium hydroxide to distilled water? Distilled water. You know, distilled water, the pH of neutral water is 7. If you would have added 0.01 moles of NaOH, that means the concentration, and we'll keep it 1 liter. The concentration would have been 0.01 molar. So the pOH, because it's a complete dissociation, the pOH is going to be negative log of 10 to the power of minus 2, which would have been 2, or pH would have been 14 minus 2, which is 12. That means you would have gone from pH 7 to pH 12, a difference of 5 units. And realize that if this is on the negative logarithmic scale, that means the concentration of the hydronium is changing by 100,000 folds. Because as you can perhaps recall from chapter 15, that with every unit change in pH, that basically means that the hydronium ion changes by 1 unit. So that's pretty remarkable. That's pretty significant. So realize that a buffer did not allow a change more than 0.05 units, whereas water, doubly distilled water, or deionized water, that will jump from 7 to 12 because of the absence of buffer in that scenario. Alright, the question here is that we have added hydronium ion to a buffer. It's exactly the same situation. I want you to think about what all has happened. And just to get you started, I would give you the equations, but I really want you to work on the math of this. I have worked the base function for you. I want you to work on the acid function, and obviously there is a reason I want you to work on how to go about the ice problem specifically for this. So realize again, we have 2 things in our buffer. We have acetic acid, which with water is going to give you hydronium plus acetate. That's my main ionization, and I have in my solution, I have sodium acetate, CH3COO minus Na plus. So if I use 0.1, that is going to give me 0.1 moles of sodium and 0.1 of the acetate, and to that I'm going to now add hydronium. So what would happen if I add hydronium or H plus. That H plus now is going to react with acetate. So hydronium plus CH3COO negative is going to give you CH3COOH and water. What does that tell you? That tells you that the acetate, because amount of hydronium added is only 0.01, and that's going to completely combine. It's going to get used up by the acetate, which is why it doesn't feature in your initial concentration for the ice. It's going to completely use up, and how much will be used up? 0.01 will be used up to generate 0.01 of acetic acid. So now all you got to do is set up your ice. You have to think about how much acetic acid is present. You were given 0.1 to begin with, but have you generated more acetic acid in the process? Aha, you will add 0.01 in this case. Acetate, you had 0.1 in the system, and since some of it got used up, you're going to subtract that, and of course the rest of it remains exactly the same. So work on the math for that and figure out what the pH of that solution would be. You should see a slight decrease in this case. So starting from 4.78 was the pH of our buffer, you will see a slight decrease. It might drop to like 4.70, 4.69 in that range roughly.